Hello everyone, I am Rupakde. Today I am going to discuss a problem on real analysis which is asked JAM 2020. Okay, so given problem is define S1 equal to alpha greater than 0 and Sn plus 1 equal to 1 plus Sn square by 1 plus alpha and n greater equal to 1, then which of the following is true. Okay, see that here S1 equal to alpha, so all terms of Sn is always positive, that is Sn is nothing but a positive sequence of real number. Okay, so option A, if Sn square less than 1 by alpha, then Sn is monotonically increasing and limit n tends to infinity, Sn equal to 1 by root alpha. And option B, if Sn square less than 1 by alpha, then Sn is monotonically decreasing and limit n tends to infinity, Sn equal to 1 by alpha. Third option, if Sn square greater than 1 by alpha, then Sn is monotonically increasing and limit n tends to infinity, Sn equal to 1 by root alpha. And fourth option, if Sn square greater than 1 by alpha, then Sn is monotonically decreasing and limit n tends to infinity, Sn equal to 1 by alpha. This is the problem. Okay, let us try to solve this kind of problem. So I start basically with how to solve this kind of problem. Okay, so this problem is also important for CSIR NET exam or GATE exam or SET exam also. Okay, so first of all, recall some basic fact. Recall first point, a real sequence Sn if Sn plus 1 greater equal to Sn for all n belongs to n, then Sn is monotonically increasing sequence of real number. Okay, second point, Sn sequence of real number if Sn plus 1 less or equal to Sn for all n belongs to n, then Sn is monotonically decreasing sequence of real number. Okay, so third point, Sn with a sequence of real number. Okay, a real number capital G belongs to R such that Sn less or equal to capital G for all n belongs to n, then Sn is bounded above sequence. Okay, fourth point, Sn with a positive sequence of real number and small g belongs to R such that Sn greater equal to small g for all n belongs to n, then Sn is bounded below. Okay. So first point is Sn is monotonically increasing if Sn plus 1 greater equal to Sn. Okay, that means Sn plus 1 by Sn greater equal to 1. Okay, and here this is nothing but Sn plus 1 by Sn less or equal to 1. Okay, if this condition is hold, then Sn is called monotonically decreasing sequence, and this sequence, a real sequence, is called bounded above if there exists a real number g belongs to R such that Sn less equal to g for all n belongs to n, and Sn is said to be bounded below if there exists a real number small g belongs to R such that Sn greater equal to g for all n belongs to n. Okay, then we can say that Sn is bounded below. Okay, and Sn is called bounded if it is bounded above and as well as bounded below. Okay, so Fifth point, Sn be the sequence of real number and capital G and small g belongs to R such that G less or equal to Sn less or equal to G for all it belongs to N, then Sn is called bounded sequence. Okay. Now recall a theorem. Okay. A monotone increasing sequence of real number, okay, bounded above, then Sn is convergent and converges to least upper bound, that is LUB. Proof left for exercise. Okay. Clear? Okay. 7th point. A monotone decreasing sequence Sn of real number bounded below, okay, then Sn is convergent and converges to greatest lower bound, that is GLB. Okay, so these 7 facts, okay, we used to solve this kind of problem. Okay, let us try to solve this kind of problem, okay, using this result. Okay, okay, so given that S1 equal to alpha, okay, where alpha is greater than 0 and Sn plus 1 equal to root over of 1 plus Sn square by 1 plus alpha, okay, and n greater equal to 1. Okay, so that is given problem. First we calculate Sn plus 1 by Sn, okay, that equal to root over of 1 plus Sn square by 1 plus alpha, okay, into 1 by Sn. Okay, and for monotone increasing sequence, that is greater equal to 1, and for monotone decreasing sequence, this term less equal to 1. Okay, okay, so if Sn plus 1 by Sn greater equal to 1, that implies Sn monotone increasing. Okay, and if Sn plus 1 by Sn less or equal to 1, that implies Sn monotone decreasing sequence. Okay, so Sn plus 1 by Sn for monotone increasing sequence, Sn plus 1 by Sn greater equal to 1, that imply 1 plus Sn square by 1 plus alpha into 1 by Sn greater equal to 1. Clear? This implies squaring both sides, we get 1 plus Sn square by 1 plus alpha into 1 by Sn square greater equal to 1. Clear? So this implies 1 plus Sn square greater equal to Sn square of 1 plus alpha. Clear? Okay, so we find 1 greater equal to alpha into Sn square. Clear? Okay, so that gives Sn square less or equal to 1 by alpha. Okay, so for monotone increasing sequence, this condition is also hold. Okay, so if Sn square less equal to 1 by alpha, then we say that Sn is monotonically increasing sequence of real numbers. Okay, and if Sn plus 1 by Sn less or equal to 1, then we find that Sn square greater equal to 1 by alpha. So if Sn square greater equal to 1 by alpha, okay, then Sn is monotonically decreasing sequence of real number. So we find two results. Okay, so first result is, if Sn square less or equal to 1 by alpha, then Sn is monotonically increasing. Two number. If Sn square greater equal to 1 by alpha, then Sn is monotonically decreasing. Okay, we find these two results. Okay, now we consider case 1 for monotone increasing sequence and case 2 for monotone decreasing sequence. For case 1, okay, if Sn square less or equal to 1 by alpha, then Sn is monotone increasing sequence of real number. Okay, now we have to prove that Sn is also bounded. Okay, so you look that Sn square less equal to 1 by alpha. Okay, that means Sn less or equal to 1 by root over alpha. Clear? And that equal to G say. So this implies Sn less or equal to G for all L belongs to N. That means Sn is bounded above. So Sn is monotone increasing plus bounded above. So from previous theorem we can say that Sn is convergent. Clear? So Sn is also convergent. Okay, let Sn converges to some real number. We say that is L. Okay, now recurrence relation is Sn plus 1 equal to root over of 1 plus Sn square by 1 plus alpha. Okay, so squaring both sides we get Sn plus 1 square equal to 1 plus Sn square by 1 plus alpha. Clear? Multiply both sides by 1 plus alpha, then we get Sn plus 1 square of 1 plus alpha equal to 1 plus Sn square. And taking limit as n tends to infinity, then Sn plus 1 is also tends to L. Okay, so L square of 1 plus alpha equal to 1 plus L square. So that gives, this gives L square alpha equal to 1. That means L equal to plus minus 1 by root over of alpha. Since Sn be the sequence of positive real number, because each term of sequence Sn is also positive, so limit cannot be negative, so L equal to 1 by root over alpha. So we conclude that if Sn square less equal to 1 by alpha, then Sn is monotonically increasing sequence and Sn converges to the limit 1 by root over alpha. Okay. So from these option, we see that option A is correct. Okay. Okay. So okay. Now case 2. If Sn square greater equal to 1 by alpha, then Sn is monotone decreasing sequence of real number. Okay. Now we have to show that Sn is also bounded below. Okay. So Sn square less or Sn square greater equal to 1 by alpha, that means Sn greater equal to 1 by root of alpha for all n belongs to n. Okay. That means you can that equal to g say. Okay. So Sn greater equal to g for all n belongs to n. That means Sn is bounded below. Okay. Since Sn is also monotone decreasing and bounded below, that means Sn is also convergent. This implies Sn is convergent and converges to L equal to 1 by root alpha. That left for exercise. Okay. So using this result, we can see that this option is also false, and that is 1 by alpha, so that is also false. That is 1 by alpha, so that is also false. So only option is A is also correct. Okay. You can also see that here, if you can also see if 0 less than alpha less than 1, that implies Sn is strictly monotone increasing sequence of real number, and if alpha less greater than 1, then Sn is strictly monotone decreasing sequence of real number. That is also these are also left for exercise. Okay. So this is the way to approach this kind of problem. Okay. I can solve this problem many ways. Okay. So I thought this is the easiest one. Okay. And I hope you got the idea. Okay. So take care and thank you very much, and subscribe my channel for more update, and again thank you. Okay.